So this is a project by myself, Amanda Tab, and Katia Laura Saint on origami constructions. The origami first originated in Japan, so this entails the art of folding paper to create objects, for example, a dog, a heart, a boat, a swan, or anything of that nature, really. There's been amazing constructions of origami, big ones, small ones. So if used correctly, we now have something called folding sequence, which is a step-by-step sequence of origami construction. They can be two-dimensional or three-dimensional. You can prove algebraic identities using origami. So the idea of origami is to fold and make crease and unfold and make another crease. From this, we can locate points of intersection from our crease lines and then try to construct geometric figures. So many geometric figures can be constructed with origami, for example, an equilateral triangle or angle bisector between two lines. Origami can trisect angles and double cubes and solve general cubic equations. This is a GeoGebra demonstration that I did that just simulates origami in different ways. So of course there's the actual paper that you can fold and do something with that nature. But there's also technology that is useful that can be used to display different mathematical concepts. So let's start with this. Here we're going to use GeoGebra to simulate paper folding to understand the workings of origami. So you're going to open your GeoGebra window, and first off, to show the labels of the created points, we're going to go to Options, then Labeling, then click New Points Only. Let's see if I can move this a little bit. Options, Labeling, New Points Only. Then we're going to type our points into the input bar. So we're going to start with A equals parentheses 0, 4, the first one. And then B is going to be 6, 4. And then C is going to be 6, 0. And D will be 0, 0 at the origin. Then to fix the location of these points, we're going to highlight them and then check fix objects so they do not move. So we're going to highlight these, object properties, and then fix object. So now they can't move. Now we're going to make a polygon of ABCD. So you're going to click your polygon tool over here, and then click A, B, C, D, and back to A in that order. So now we have our polygon here. Then we're going to click Point on Object to create a point on the interior of the polygon. So Point on Object over here. Click the inside. Now we have E on the interior of polygon ABCD. Now we're going to drag the point to 4, 2. So 4, 2 right here. So if we fold the right corner of the rectangle at the top, where point B will coincide to E, the crease will be a perpendicular bisector of BE. So let's see here. To construct the perpendicular bisector, we're going to do the perpendicular bisector tool. It should be right here. Then we're going to click point B and then point E. So point B and then E. And then using the intersect two objects tool, we're going to construct our points F and G. So intersect point, intersect tool. So we're going to click here and here. And now we have our figure drawing right here. And now we're going to, oops, sorry about that. We're going to hide the axes for a second. as we drag, so first we're going to drag this point to 5, 0. And then intersect this line right here as we hide the axes first. And we're going to pick intersect and right here. So now we have a point H. We can put the axes back. And then we're going to drag the point to 1, 3 up here. Then we're going to use the intersect tool to intersect right here. So we're going to hide the axes first. So we have intersect down here. Now we have I. Okay, so now we can put our axes back. Now we're going to we're going to hide the perpendicular bisector. So we're going to hide this here. We don't need that. Now we're going to drag the point to 5, 0. E to 5, 0. Oh, I'm sorry, I skipped it. Hide is 5, 1. So sorry, we're going to place this on 5, 1. Now we're going to construct a polygon from FEG. So we're going to go to polygon tool, F, E, G, and then back to F again. So now we have this triangle on our screen now. Now if we drag the point E to 5, 0, notice that it disappears. So you can see that here. So that's because point F, which is the intersection of the perpendicular line in AB, does not exist anymore. So we're going to draw the corner of the folded paper with vertex E, so we have to construct a perpendicular to GE and passing through E. So we're going to go to our perpendicular line right here, perpendicular line. So we're going to click, we're going to do GE, passing through E. So here and here, perfect. And then we're going to draw the other vertex, so we construct a line parallel to GE passing through H. So parallel to GE and passing through H. So like that. So we have our parallel and our perpendicular. Now we're going to intersect the two new lines forming J. So we have our intersect tool right here, and we're going to intersect right here. Perfect. So if we drag the point, okay, so hide, okay, now we have to hide the lines, I'm sorry. So we're gonna hide these. Show object, show object. Now we're going to construct a polygon, EGHJ. So polygon, E, G, H, J, and then back to E again. So now we have this right here. So now we're going to drag the point E to 1, 3. And we're going to do the same method. So we're going to construct a perpendicular line to EF passing through E. So perpendicular to E, perfect. And now parallel, like the one before, parallel line to EF passing through I. Here we go. And now we're going to intersect the line down here to make K. Perfect. Now we're going to hide the two lines. We're going to hide this line and hide this line. And now we're going to make a polygon EFIK. So polygon tool, EFIK, and then back to E again. Now we can drag the point E anywhere inside the rectangle to simulate the origami folding. Let's try it. Voila. So now if we drag it inside, we can simulate as if we have a piece of paper and we're folding it like this to create an origami figure or to create the beginning steps. Thank you. So this demonstrates the different ways you can see origami and how the paper folding is super interesting on a different platform. As for the methods, so as I said, GeoGebra is an example of using technology to demonstrate mathematical concepts and skills. And this can be used for many different aged classrooms. So I'm thinking that maybe a first grade classroom wouldn't be able to make a GeoGebra applet like the one I just did, but I'm sure they'd be able to follow it in some context as they can imagine a piece of paper in front of them and how it folds if you pull the corner down. And then in an advanced classroom such as high school or first year college, undergrad, the students would be able to make this construction in GeoGebra and be able to understand the different algebra concepts and geometric definitions and figures, as the coordinate plane is definitely used a lot in GeoGebra, and the different points and point intersection as well. So there are different methods for origami, such as Haga's construction that was discovered by Kazuo Haga. This requires only a single diagonal crease and can also produce all rational fractions. Many different mathematicians also contributed to Haga's method and even built off of his. And I thought it was interesting to see how just a small contribution can just blow up into different things as people can use inspiration. So Haga's method differs from others in that the paper is not unfolded between all folds. That's interesting to me because the origami that I built in this presentation is definitely different than that, in that I unfolded in order to make certain creases. So let's go into that. So this is a video that I did of the start of an origami 3D cube. Right, so this is the first side of the 3D cube, and then over here you can see the other 5 ones that I had to make in order to make the 6-sided cube. So in the previous video, I took a square sheet of 15 centimeters and started with the first fold by folding it in half. And then I followed the steps from there. I proceeded with specific instructions with the directions of making creases, unfolding, and folding. It's actually pretty intricate, but it was a good cube at the end. It was very interesting. At the end of the video, the first side of the cube was complete. Then I proceeded with making 5 more sides to make the 6 sides of the cube. And here is the cube on the right that was the results. And here is a YouTube video of one of the algebraic identities that can be proven with origami. So let's get into that.
Double your pleasure. Double.
Another add. Let's make this small.
Hi, welcome to today's video. Today we are going to discover math in origami. Origami first originated in Japan. We can create many beautiful shapes using origami. We have seen paper frogs, birds, boats, and so on. But it is less known that origami is strongly related to math. Origami is powerful because we can achieve beautiful creations in origami that we cannot achieve using ruler and compass. For example, a person can trisect an angle divided into three equal subangles using origami. Origami has its own principles and definitions and axioms, known as Fujita-Hattori axioms. Some people create three-dimensional forms out of origami, while others prove Pythagorean theorem using origami. Today, let's prove an algebraic identity using origami. Let's start by making a sailboat. So I have a paper over here. So now I'm trying to cut out a square shape from this paper. So now I'm going to create a fold over here. I'm going to fold it the other way as well. And I'm going to make a small fold over here. So now I'm going to open this. So here is our sailboat. So you can see this is our sailboat. Now when we unfold this boat, we get lines as such. So I'm just going to highlight the lines so you can see them. Now we have obtained two squares and two rectangles. So what about the fold lines? Do you recognize them? Yes, they are perpendicular lines. We have also two right triangles over here when we fold along the diagonal. So thus we see geometry is being unfolded in our origami creation. Now let us take this length as A and this length also as A, and this as B, and this as also B. And let us take the four corners as A, B, C and D. Now let us consider this as first square, second square, third rectangle and fourth rectangle. So the area of this square is A into A, which is A square. The area of this rectangle is A times B, which is AB. The area of this rectangle is A times B, which is AB. And the area of this square is B times B, which is B square. Now let us prove our algebraic identity from this origami creation. We know that area of ABCD is equal to AB times AD, and AB is equal to A plus B, and AD is equal to A plus B. And area of ABCD is area of first square plus area of second square plus area of third rectangle plus area of fourth rectangle. So I have written here AB is A plus B and AD is A plus B, and area of ABCD is area of 1, area of 2, area of 3 plus area of 4. So we have A plus B times A plus B is A plus B the whole square, and area of region 1 we know it is A square. Area of region 2 is B square, area of region 3 is AB, and area of region 4 is AB. So I have written area of 1 is A square, area of 2 is B square, area of 3 is AB, and area of 4 is AB. So now we have A plus B the whole square is equal to A square plus B square plus 2AB. And that's how we can prove an algebraic identity using origami. So go ahead, fold paper and get a good grasp on mathematical concepts. Thank you for watching.
So let's do this. Back to the PowerPoint. So that was a little bit of background and information with the math and incorporated with the origami creations.
Stand up! Act like stand up! Stand up! Stand up! When I move, you move. Just like that.
Okay. Hi, welcome to today's video. Today we are going to see
Okay,
part 2
second.
of the
Replay.
topic Discover Math in Origami.
Yeah. All right, there we go. Okay, so back to here.
Okay, as Amanda said before, I am Katia, and today we are going to demonstrate on how to basically construct cube root of 2 using the Belloc square. So these are some steps that you can follow when constructing cube root of 2. The first step would be using the coordinate axes and label O as the origin, and then the y-axis, we would call it R, and the x-axis, we will call it S. Now pick 2 points and plot those points, A and B. And for this example, we are going to let A equals to -1, 0, and B will equal to the coordinate 0, -2. Now construct line R prime at x equals to 1 and S prime at y equals to 2. Once you have done that, you would be folding A onto R, which will create creases that crosses line R at point X. And it doesn't have to be X, but for now, we're just gonna call it X and Y. And B will be folded onto S prime, which will create a crease that crosses line S at a point Y. You will notice that XY is perpendicular. Oh, I am so sorry. I have a little one and he wants his mommy's attention. I'm sorry. You will notice that XY is perpendicular to segment A prime, and B prime. And when we connect them, there will be 3 similar right triangles that are created. We would have triangle OAX, OXY, and OBY. Now, to solve that, We are going to let the absolute value be the length of the segment. And again, we are using absolute value because the length has to be positive. So then we have absolute value of OX over the absolute value of OA equals to the absolute value of OY over the absolute value of OX equals to OB over the absolute value of OY. And again, we are using absolute value because we need to have positive side length. And also we're setting those proportions because again, similar triangles, similar right triangles, we can set a proportion to find the side length. Substituting 1 for OA, if you go back in a few minutes, you will see we did use -1, 0 for point A, so the distance would be 1 unit, and 0, -2 for B, so the length of OB would be 2 units, and we would end up with OX equals to absolute value of OY over absolute value of OX equals to 2 absolute value over the absolute value of OY. And this is because we substitute 1 for OA and then 2 for OB. Finally, we would compute this by multiplying. We end up with OX cube equals to the absolute value of OX times absolute value of OY over the absolute value of OX times 2 over the absolute value of OY. And when we not cross multiply, but when we cross these out, you will notice that the absolute value of OX or cube is equal to 2. Taking the cube root of both sides, we end up with segment OX or OB, no, it's OX equals to cube root of 2. And we have a video to demonstrate how we did this. So let's just get into that. Hello, hi, my name is Katia in partnership with Amanda. And today I am going to demonstrate how to use origami to basically solve cube root of 2. We will also be using Billock square to solve it or to demonstrate it. As you can see here, we have our coordinate plane with O at the origin, and then the y-axis is the R, and the x-axis, we are going to call it S. So to start, we are going to use point A, which we'll call it -1, 0, and point B, we are going to call it 0, -2. So let's plot point A at -1, 0, call this A, and point B right here, -2, 0. Next, we are going to, I guess you could say we are going to reflect it over the y-axis. So it will be at x equals to 1. X equals to 1. And we are going to call this R prime. And we are going to reflect this over the x-axis. So it would end up being at y equals to 2. And we are going to call it S prime. Now what we are going to do, we are going to take the sheet of paper and then fold it. Remember, it's origami, so there is folding involved. We are going to fold it and make sure that A falls on R prime, and then B must get to S prime. So let's fold it, and it's not gonna be perfect the first time, but there's nothing wrong with trying. So right here, and we need to make sure A and B, A falls on R prime and B falls on S prime. Let's move it a little bit. It's almost there. Let's see, B is almost there, so I just need to adjust it a little bit more. And I think I may have it. And of course, there will be creases that are created once we fold it. As you can see here, A is right on top of R prime and B is on top of S prime. So now let's mark them so we don't lose the location once we open the paper back. It's right there. And this point we are going to call it B prime, and this will be called A prime. And notice here we have a crease. This crease, it will be perpendicular. Let me readjust the crease. Here's our crease right there. Go. Okay, so let's draw the line here, and this line will be perpendicular to our segments. Our two segments. In a few minutes, or a few seconds, I will show you the segments. And we have segment A prime, and segment B prime. This is one of the segments, and this where the crease line intersect S, we are going to call it Y, and where it intersect R, we are going to call it X. So now let's measure the distance of XY, or the segment XY. Let's measure it so we can see how long this thing is. It is approximately 2 centimeters long. So, and of course, we know from elementary geometry, a square is congruent on all sides. So if one segment is 2 centimeters, we need to make sure all the other segments are, this one actually went over a little bit. Right here, it's 2 centimeters. And then I'm going to measure 2 centimeters from this segment also. I have 2 centimeters right here. So now connecting our square. Right there. Just a little bit more. Here's our square. Over. Okay, right there. Now, from this, you will notice 3 special right triangles are created. 3 special right triangles are created. Don't forget, this is A. It kind of went over the line there. But if you trace this, you will see we have a special right triangle right there. Another right triangle at right here. And then we should also have another right triangle at OBY right here. Like this right there. Hopefully you can see it better in the camera. Right here, there's one. And then this is triangle OAX. And then we have triangle right here, OXY, right here, OXY. And then our last triangle, right triangle, is from here at OBY, right here. Triangle OBY. Now, since we have similar right triangles, we can set up proportions. And we are going to set up the proportion as OX And its absolute value, because since we are dealing with side length, they must be positive, and the absolute value of any number is always positive. Just a little reminder. OA equals to OY over OX equals to OB over OY. Now, don't forget, this was 1 unit long. OA or AO was 1 unit long, and OB was 2 units long. So wherever I see OA, I'm going to plug in 1, and OB will be substituted with positive 2. So absolute value of OX or OA, I'm sorry, OA is 1, and absolute value of OB is going to be 2, which will end up being absolute value of OX equals to the absolute value of OY OY over OX equals to 2 equals to 2 over OY. Now solving this, computing this, we should end up with OX cube equals to OX, absolute value of OX, times OY over OX times 2 over OY. And when we compute this, notice here, this crosses out, that crosses out. We have the cube root of OX equals to, well, not the cube root, OX cube equals to 2, I'm sorry, equals to 2. Now taking the cube root of this, we end up with OX equals to the cube root of 2. And if we go back here, OX is the y coordinate. So in turn, we end up with 0 cube root of 2. And this is how you would use origami, specifically the Bullock square, to come up with the side length of this right there, from the origin to where the crease intersect the x-axis or line R, and it ended up being cube root of 2, or another way of solving doubling the cube or finding the cube root of 2. I hope this makes sense for you. And until next time, thank you again. This is Miss Lorison in partnership with Amanda. Thank you. Yes, so again, that was just a demonstration of how you would construct the cube root of 2. And the next one, we are going to go over how we would use origami and the Bullock square, and also Lil's method to solve cubic equations like polynomial to the 3rd power. So again, we start with the steps, but this time we are going to use the turtle analogy. Ho's the one who started with that, and of course we would use the origin, start at the origin, and we would be going in the direction of the positive x-axis, and then using a straight edge or a ruler, draw the first coefficient of the polynomial along the x-axis, a sub n, and it would be a sub n unit. Turn 90-degree counterclockwise and draw the distance of the next coefficient. Repeat this process until you end at point T. The first point, we would call it, well, whatever you want to call it, whether you want to call it A or O, whichever letter that you want to use. But for this purpose, we will use T, and the last coefficient would be sub naught, or the constant term. And if any of the coefficients are negative, then we basically go backwards. And if any of the coefficients are zero, one term is missing, then the distance would simply be 0. And instead of using or giving you an example, like I did on the other one, we are just going to use a video from YouTube that not only use the Belloc square, but also use the Lil's method. And it's with the Lil's method that
I've been getting paid
get
$1,000 a month, if not more.
with the Lil's method, we get the turtle analogy. So let's watch
So
and
I got requested
and see.
question just because some people had some problems with the technique. So the question I've been asked to solve is this one here: x cubed minus 6x squared plus 11x minus 6, and the roots of this are of course positive 1, positive 2, and positive 3. So since these are all real roots, we should be able to solve for them with the method. So I'm just going to go and sketch this up quickly. I'm not going to explain all that I did in the previous video, but I'm going to try to say out loud what I'm doing as I go. So I'm just going to go ahead and draw up the problem. So I'm just going to start here. So I'm going to call that point A. And so our first coefficient is the coefficient of x cubed, which is just positive 1. So I'm going to be heading in this direction. So that means I'm going to head 1 centimeter across, which is just 2 grid squares. Yep, just there. And so that's A3, and its direction is that way. The next coefficient is negative 6. And so we want to turn 90 degrees anti-clockwise at each coefficient. So if I turn that way, we'd want to head in that direction. However, since it's a negative coefficient, we're going to head down the other way. So I'm going to go 6 units down, which of course I'm using centimeters because that's what this grid is in. So down to here, and so then that's A2, and I've got the arrow heading up to show where the positive direction would be, but we've of course headed in the negative direction. So the negative coefficient is positive 11, and so now we're going to turn 9 degrees anti-clockwise again, and so it's positive, we're going to head that way, cool. So let's draw that out. Cool, we got A1 there, positive direction, and then we want to turn 90 degrees once more. We're heading there, but the last coefficient is negative 6, so we're going to head 6 that way. So let's just draw that out. Cool. And this is of course going to be point B because this is our endpoint, and it's also the A0 coefficient. So now we just need to draw our R dash and S dash axes. So of course we recall that in order to do that, so for R dash, we find our A2 line, and then we move a distance equivalent to A3 on the other side of it and draw a line parallel to A2. So we can see here, it's 1 centimeter across. So I'm just gonna do a line 1 centimeter the other side of A2. Cool, let's draw that down. And then similarly with S dash, that's going to be A1, but A0 the other side of it. And so that was 6, so let's just go 6 down, which is on this grid line. Bring up so you can see it. Yep, cool. So now let's just rule that across. And so let's just label these. This is R dash, and this is S dash. And so now we're just going to make sure we follow the method, which requires us to take A onto the R dash axis while simultaneously taking the point B onto the S dash axis. So let's go ahead and do some folding. So I'm just going to fold it over. And so my strategy that I use for this is I try to place A on R dash first, and then try to slide it up and down until B meets with S dash. So I'm just going to chuck A onto R dash, which is it's on there. And so B, so A is there. And so B is not, oh, it's pretty close. So let's give it a bit of a slide. So still want to take it a bit. So about there. And so now I'm going to fold this out. And so if we just take a peek, we see that B falls onto S dash there. And then we see that A falls onto R dash there. And so you could do a little trick by poking a hole through the paper on points A and B, and then you can kind of see the axes on the other side, but I had a bit of difficulty with that, but I don't know, give it a go, it might work for you. So now I'm just gonna take note of where these intercepts are. So this is pretty much dead on the intersection of R dash and S dash, and so I'm gonna call this point B1, and then A, that's here. And so I'm going to call that guy A1. And so now let's go ahead and draw our lines. So I'm just going to link these up. And I'm going to need a slightly bigger ruler for this. So I'm there, and remember, along our fold, which should be perpendicular to both of these lines, we just want to draw a line straight through. So let's go. Yep, cool. And so now you can get the angle theta in here, here, or here. So let's just take it in here, theta, and straight away you can see, oh, hold on, this ratio is 1 to 1. So the opposite side is 1, the adjacent side is 1, and we recall from the previous video that our roots are of the form x equals negative tan of theta, and theta is of course the same as the opposite side over the adjacent side in a right angle triangle. So here it's negative, x equals negative, and so the opposite side, so remember we had to go negative down this line, so this would be negative 1, and this is 1 along a positive axis, so it's just positive 1 along, so therefore, our root is simply 1, which is one of the ones we were looking for. So cool, let's find the next one. And so now I'm just going to keep sliding A up R dash. Okay, let's see. So I've got A on there, but B is out in open space at the moment. So that means I need to keep sliding A up. So let's see, A, where are you? So B still needs a bit more. A's on there. Okay, so B has found S dash. Let's just confirm that. So we can see B, he's just poking out there. A is just on there, so cool. So let's make a note of where those ones are. So, hold on, so, yep, so we'll make little line there, and then with B we'll make a line here. Cool, so now once again we just got to draw our lines. Cool. So sorry, this is a bit tedious, but I mean this is how the technique goes. And so again, let's just draw our horizontal line that, or not horizontal line, the line that is perpendicular to both of these. And so now let's take a look. So I'm going to measure up here and measure along here. So now let's go, this is about 2 oh no, so you see the intersection there is about 2.1. So x equals negative 2.1 over, and we know that this is just 1 along here. So then this gives us a root of 2.1. And so I kind of skewed my choice over here a bit to show you that because we're all humans here and we're folding paper, this can be prone to error. So of course and so the error is just because say I've got dots here and then trying to align them onto other axes, we can be a bit off but quite close. So see here 2.1, we know that that's not a root because we know that the proper root should be positive 2. However, if we're really careful, say if we intersected right on here, I imagine that this line would have gone straight through there, which would have measured 2 on here, which would have given us exactly 2. But as we're all just humans, my folding was a little inaccurate here, and so that's a limitation of the technique. So it may be able to give you a good guess, but if you're looking for something that's dead on with many decimal places accuracy, this technique is not quite feasible for that with the current way of applying it. I mean, the technique is good. The problem is with the humans applying it. So now let's find the final root. And so I'm going to keep sliding A up. So let's see. B is about there, A is about there. Righto. So I'm going to follow that. So I'll just show you. So B is right on S dash there, and then A is right on R dash there. So now again, let's mark these points. So here is A3, and then here is B3. Cool. So now let's just go ahead and draw lines. Got one there, and B3 is there. And now, because you've done so many folds, you've got to find the one that's perpendicular to both of your lines that you did. And so it looks like the one that hasn't been ruled is this one. So let's just make that a bit more prominent. Yeah. So now let's go ahead and rule that. There we go. Cool. And so, as I said, you can keep taking an angle in here, but just for argument's sake, let's take it in another location. So I said you could take it here or here. So let's take theta in here. So let's measure this side. So this side measures up to 6 centimeters, and this side measures up to 1.8. It looks like about there, even though the intercept is about there on 2. So so we'll call that 1.8. So then if we go opposite over adjacent, so then x equals negative. And so remember, this is a negative axis again. So we've got negative, so that's 6 over 1.8 x equals, and so then negative 6 divided by 1.8 is of course something that doesn't come to my mind right now, which is probably something like 3.3 or something like that. Let's just do that properly. So yeah, and so it was something like 3.3 recurring. So you can see that, yep, that's pretty close. Again, if you're more careful with your measurements, say here, we noted that the intersect was straight on here, and so that would have given us a ratio of 6 on 2, which would have given us the exact root of 3. So these inaccuracies here, they kind of explain why some people may have noticed multiple solutions that they could have solved the problem with. So say they may have found multiple points that worked. What I believe you would have found is through inaccuracies of applying the method, you would have found points kind of in a neighborhood around here and in a neighborhood around here. And so you get an answer that's kind of close to 3, but you're not quite dead on. And because, say, dots are large and everything, you might get quite a few ones that look like they're different solutions, but they're actually close or a bit further away from an accurate solution. So there you go. Hope that helps. Let me know if you have any.
Okay, so as you can see, even though his last 2 roots were not exactly, but the Lil's method basically gave you an exact solution, especially if you're using GeoGebra or some type of computer software. But of course, basically, using the Bullock square in the Lil's method and using negative tangent of theta, you should be able to compute any polynomial to whatever degree that it is. Next.
So, in conclusion, origami can be used in classrooms of all ages. Mathematical methods can be examined to find the best folding sequences. Technologies such as GeoGebra and teaching tools such as YouTube can be used as resources for learning the complexities of origami designs, as it is a great hands-on activity for learning and for teaching as well. I hope you enjoyed, and thank you so much.
Thank you.